G'day everybody, where's Wally here? Well, here we go again. Must be round 3. Well, Antonio said a stupid thing or 6. Cosmic Surfer did warn me that this last video of mine might bite me, and well, I'm failing to see how, unless he meant that it's going to cost me another couple of hours to tell Antonio that he's wrong all over again. That's probably what he meant. Okay, enough of that. Let's get into it. Here comes the silly. For those that make it to the end, I will have a mystery guest, someone who loves to stare out into the inky void with telescopes. I won't tell you who, you'll have to get there to find out. I also noticed, Antonio, you didn't see my video on the tunnel vision, and I guess you probably need to look at that, but then again, it does have a whole pile of moon gravity stuff on there. I guess there's a lot of backlog you've got to deal with yet. We're still waiting on you to do the red tube experiment, Antonio. When are you ever going to do that? You promised us 6 months ago you're going to go up a mountain and do that.
Wonderful. Here, now we're going to talk some more. We're going to listen to Where's Wally.
Rods don't see in colour, which is true, and why we only see in low light, we only see in black and white.
He just said in low light we only see in black and white. Do we really? He's quoting as he's speaking as if he's quoting me, and then it slips in this, like, no, you don't only see in black and white in low colour. That's a stupid thing to say. You can demonstrate that that's not true. But he needs it to, because the moon, most moons, I should say, especially moons that are not yellow, or not harvest moons, don't show colour. So the rays refracted by the lens, and well, they do this. Now the theory says we see upside down. You've heard this, you've had this taught to you. You've had this taught to you because when you look in a camera obscura, the image is reversed. So what must be happening is, here's the opening, and here's the opening, and the light from the top there must be coming to the bottom, and the light from the bottom here must be going to the top, and here's the focal point. Therefore, it's at this point you should ask the question, is the focal point at the meeting point, before or after? You see, for it to be actually inverted, it has to be after. You see, here's a quick little explanation. Here's bottom, okay? Look, bottom, and here's top. Yeah? Okay. Here's bottom, and here's top. If the image is captured here, okay, like, well, this is still bottom, and this is still top. However, if the image is captured after the focal point, then it crosses over, so that this is now top, and this is now bottom, which would be inverted. Do you see? The rods of the eye, which are only photoreceptors to receive or inform the brain of how much light is coming in, not what quality of light, simply how much, the intensity. Now, according to Where's Wally, the rods, they only see in black and white. Here's some information for you, Where's Wally. The things that determine colour and sight are the cones, not the rods. Can the cones portray black and white? Yes. How do they do that? Well, by receiving light frequency that has the same level of green, blue and red. And that says white. You see, it's not the rods, you freaking silly boob. But I'm going to show you with geometry for you to understand a little better. Okay? Now, you see in the drawing that I've just done, and the drawing that I've just done is simple, straightforward light theory. Okay? Which says this is what happens to light. Okay? Does this also happen to light? No. It doesn't illuminate these regions, does it? No. Why not? Because it's refracted by the lens, so it doesn't reach these regions that are populated only with rods.
You do actually use your whole retina, Antonio. And here's how you know. Firstly, do a blind spot test. Cover your left eye, look straight at a little light of something, and then that means you're using your fovea to see it because you're looking straight at it. Now, moving the spot that you're looking at, start looking to the left a little bit more, and you get about 10 or 20 degrees away from the light, and the light disappears because that light is now falling on the blind spot where the optic nerve runs through the retina. Now, if you keep looking a little bit further to left, now you can see the light again because it's now falling on the retina on the far side of the blind spot. Quite simple, hey? And you can also run this little program called iScream. Now, it is a fields test. This is what your ophthalmologist does when you go for a test of your retina, not your fovea, the whole retina. And basically, you look straight ahead, and it flashes little flashes all around the spot, and you press a button every time you see a flash because it's your retina with the bit with the rods on it that's registering that you're seeing a little piece of light hitting out somewhere else on the retina. So you can try this yourself, download the little program, I'll leave a link in the description, and it's a way of testing your rods on the retina. Give it a try, Antonio, unless of course you've got tunnel vision. So you're very wrong when you say that the light does not hit other parts of the retina. It does, and it allows you to see. So check it out.
Wonderful. Do you understand? For your idea to be true, which says, under low light, only the rods can transmit white information. Like, oh really? So somehow there's a low light that makes it so that it doesn't still refract? Is that what's happening? It stops refracting. Now, yes, if the pupil is wider, then this is going to be wider, but it's still going to get to the same point. That the point of the eye is to maintain the size of the aperture and the distance or the focal length at a ratio that keeps working. The eye can do this to itself, and it can also do this to the lens, okay, to keep that relationship working. Your idea, Wally, which is that, well, at some points light no longer refracts through curved convex lenses. No longer, no, it just goes straight through. And the information that arrives at the fovea with all its cones, they just ignore that. They just say, pretend you're not seeing colours. You frickin' dim-dim. You understand? This is your theory, and according to your own theory, your globe theory, you're wrong. And ophthalmology is not a finished science. You understand? It's a study of sight. It's no absolute conclusions. You understand? They're still looking and investigating.
Woo there, Antonio. You're attempting to do your usual get-out-of-jail-free card by saying that science isn't settled. Well, science by its definition is never settled. It's always learning because it's not, a religion or something like that. But what you're trying to do is be a little bit sneaky here and say that it's not settled and therefore no one knows anything, which is not true because science, in this case, probably knows about 99% of this stuff. But what you're saying is a little bit sneaky and deceitfully wrong. The function of the retina is very well understood, and I'm sure Ophthalmology 101 Day 1 is all about the retina.
Wonderful. Does it really arrive upside down in the brain? Does the brain then flip it? Is that what happens? Is it this region, this optic nerve, if you follow that filament, it goes towards the bottom and render information here at the part of the brain that renders information? And it's all still just theory. And it's always theory that tries to support the globe, because it can't be theory that contradicts the globe. That would just, well, you wouldn't get your PhD. So, dim, your own theory says you're wrong. Your theory says you're wrong. Okay?
And Antonio, I did see that you haven't looked up Averted Vision yet, have you? Now, at the end of this, I'm going to link to a little bit of video I found from a telescoper who basically has given a nice little instruction on how to use your Averted Vision. And He also talks about just how this works and why it works. And this averted vision is a technique used by literally thousands of people playing with their optical telescopes. And here is my mystery guest to tell you what he also does.
Okay, Emma, show Daddy where the Celestron telescope is. Good girl. Now show Daddy where the equatorial mount is. What a good girl. Now show Daddy where the refractor is. Where's the refractor? What a good girl. And I'm sorry, Antonio, but where's Wally is correct. Astronomers do use averted vision when looking through eyepieces of telescopes because it allows them to see dim objects more clearly. And I'm not speaking because I read something on YouTube. I'm speaking from personal experience. As you can see, I have real telescopes. And when you're using averted vision, you basically see black and white. However, when using an astronomy camera like this, we get the images in true color.
Okay, let's wrap this up. Let's have a look at the scorecard. The field test proves that the retina is used for vision. Averted vision proves that low light is seen better by rods and not cones. Antonio has proved he has no idea how an eye functions or how a lens works. And finally, Antonio has admitted that a moonlight is just normal polychromatic white light, which is what this whole thing was about in the first place.
How your eye works, using averted vision. An overlooked skill among new amateur astronomers is the art of seeing faint objects, whether it's with your unaided eye or with optics. The fact is, if you just head out the back door and walk up to a telescope, and look at a faint galaxy or nebula in the eyepiece, you'll likely not see anything at all. To see the subtle detail in faint celestial objects, you have to condition your eye and learn to use it to expose the most sensitive parts of your retina. First, a little background on how your eye works. The retina of your eye has two types of light detecting cells. These are rods and cones. Cones detect color under well-lit conditions and are densely packed in the fovea near the center of the retina. Cones help you see color and fine detail, which is why you look directly at objects when you want to see well, like books, movies, and faces. Rods are mostly away from the center of your retina. You see less detail and no color with the rods, but they're much, much more sensitive to light. The way your eye is structured means that you see the faintest objects if you look 8 to 16 degrees off-center. The exact angle is a little different for each person, and this only works if the object you're looking at is on the noseward side of your face. So look slightly rightward with your right eye and leftward with your left eye. This technique is called averted vision. It exposes the most sensitive part of your eye and lets you see fainter objects. Using averted vision only works if you avert your eyes in the right direction. Do the reverse and you'll expose the blind spot of your eye and you won't see a thing. If you're using both eyes, like with binoculars, looking only sideways makes one eye more sensitive at the expense of the other. The solution is to look up. That uses another rod-rich part of your retina above the fovea. With a little practice, averted vision can reveal objects that are 20 to 40 times fainter than direct vision. That's a huge difference, and you'll be amazed how much you can see. And one more thing, the rods in your eye are more sensitive to blue-green light, but your optics nerve and brain are not wired to detect color when only your rod cells are exposed to light. That's why fainter objects in a telescope appear grayish-white. You won't see color in galaxies and nebula like you would see in a photograph or from a huge telescope.